Everyone, welcome back to our channel Acadecia. So far we have covered mathematical operations and their properties and few types of matrices along with their properties. So today in this video we are going to learn special types of matrices. Special types of matrices. Okay, let's start with idempotent matrix. What do you mean by idempotent matrix? Suppose if we are given a matrix called A, which is a square matrix. Now, a square matrix A, if it belongs to idempotent matrix, then what is the condition? It's like A is equal to A square. When any matrix such as A, when it is given, if we multiply A matrix 2 times, it will be A square. If A square is equal to matrix A, then it is known as idempotent matrix. Okay. Next, involuntary matrix. Involuntary matrix. Here, if we are given any square matrix such as A, what is the So if we are given a matrix A, which is a square matrix, then the condition A square is equal to I. Okay, suppose if we are given a matrix A, what we have to do is we have to multiply 2 times such that it will be A square, and this A square must be equal to I. I is nothing but identity matrix. Okay, so the conditions what we have to check over here in these matrices is, suppose when we are given a matrix called A, then what we have to check is simply we have to multiply the matrix A 2 times such that we will get A square. If A is equal to A square, simply we can identify that it is an idempotent matrix. Along with that, if you want to check whether it is involuntary matrix, simply find A into A, that is A square. Check whether A square is equal to I. I is nothing but identity matrix. We have next nilpotent matrix. Nilpotent matrix and as well as periodic matrix. These two will be of similar type. Okay, the condition is A power P is equal to 0. And here the condition is A is equal to A power K plus 1. So from these conditions what we understood is, suppose if we are given a matrix called A, immediately what we have to find is A power 1, A power 2, A power 3 and so on. Okay, and what the thing you have to apply over here is A power P is equal to 0, where P is a natural number. Okay, so if we are given a matrix A, then if it is A square, if you find, then if A square is equal to 0, then the P value will be fixed as 2. Okay, the condition we have to check is A power P is equal to 0. For what value of P the matrix of A will be 0, that value of P is known as index. Index. Okay. Similarly, this periodic matrix as well. If we are given a matrix A, we will find A square, A cube and so on. Okay. For what and so on. And where K is a positive integer. K is a positive integer, and what the condition over here is A is equal to A power K plus 1. If we are going to find A square, A cube and so on, if you find, we have to check out that when this A is equal to A power K plus 1, I mean for what value of K will this matrix will be equal to the original matrix. Suppose if we are given A matrix, and if we are finding A power 1, A power 2, A power 3 and so on, if we find, suppose for value 3, if A cube is equal to A, then what will be K value? This is, we have to compare with this equation. Like A power K plus 1 is equal to A cube, then K plus 1 is equal to 3, then K will be 2. here we have to decide the k value, and this k value is known as the period of a matrix A. Next is conjugate of a matrix. So, from the chapter of complex numbers, you will find the word conjugate. What it is if we are given a matrix A, then the entire element should be of complex numbers. Okay, for complex numbers only we can find the conjugates. Okay, for a complex number, suppose if we take a complex number 1 plus 3i. Okay, for this, what will be the conjugate? It will be 1 minus 3i. Simply we have to interchange the signs. Okay, a is equal to 1 plus 3i, 5 minus 6i, 7 minus 3i, 8 plus 2i. If we are given a matrix called A like this, in terms of all conjugate numbers, I mean complex numbers, then how to find the conjugate of this matrix? The conjugate is represented by A bar. Okay, then A bar will be, we have to simply interchange the signs. Okay, it's like 1 minus 3i, 5 plus 6i, 7 plus 3i, 8 minus 2i. Simply we have to interchange the signs. Okay, now let's see what will be the transpose conjugate. Transpose conjugate means already we have learned what will be a transpose of a matrix. Now just transpose conjugate of a matrix. What it is transpose conjugate. From the name itself, what we have to do is, first we have to find the conjugate of the given matrix and then we have to transpose that. Suppose take an example of this only. If we have this matrix A, first we have to find A conjugate first. So from A we have to find A conjugate. After that, for this we have to do transpose. Okay, then transpose conjugate of a matrix is denoted by A theta or A in the power we have a star. Okay, now let's see what is the A transpose conjugate of this matrix. It will be like we have to first arrange this conjugate. I mean we already have a conjugate. Just we have to transpose this into rows and then columns. 1 minus 3i, 5 plus 6i, 7 plus 3i, and then 8 plus 2i. Okay, simply what we have to do is, we have to find a conjugate for that and next we have to transpose it. That is conjugate and then transpose conjugate. Next is Hermitian matrix. Similar to that, we have Skew Hermitian as well. The thing is, A power theta is equal to A and here A power theta is equal to minus A. This is nothing but a transpose conjugate of a matrix. If the transpose conjugate of a matrix is equal to the given matrix A, then it is known as Hermitian matrix. And here the conditions apply. One note is there. That must be important. All the principal diagonal elements must be real. Okay. And coming to the Skew Hermitian matrix, it will be all the principal diagonal elements must be imaginary or else it can be 0 as well. Okay. For the Hermitian matrix, what it is the transpose conjugate of a matrix A must be equal to the original matrix A. And for the Skew Hermitian matrix, it's like the transpose conjugate should be negative of the matrix A. Suppose if we take an example, we can easily solve this Hermitian. Moving on to the next, unitary matrix. Unitary matrix. It's nothing but A into A theta is equal to I or A bar theta into A. This is the condition. Don't you find it's quietly similar to the orthogonal matrix? Its orthogonal matrix is nothing but A into A transpose, or A transpose into A will be equal to I. Here nothing but, instead of transpose, what we are using? Transpose conjugate we are using in the unitary matrix. Okay, what we have learned in idempotent matrix? A is equal to A square. Okay, in involuntary matrix, A square is equal to I. Nilpotent matrix, A power P is equal to 0, where P belongs to natural numbers. And in periodic matrix, A power K is equal to A power K plus 1 is equal to A, where K is a positive number. Conjugate, A is equal to A bar. And transpose conjugate, A is equal to A power theta or A power star. And Hamilton, A bar theta is equal to A, and this is A bar theta is equal to minus A. And coming to unitary, it's A into A bar theta is equal to I. Okay, that's all for today's video. If you like the video, please like, share and comment and subscribe to our channel. Thank you.